Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 1.7 on inequalities. So let's start off by doing a quick review of what an inequality is, and it's very similar to an equation. The only difference is that now it's not two expressions joined by an equal sign, it's going to be two expressions joined by an inequality symbol. And there are four inequality symbols in total. We've got what are called the strict inequality symbols, which is less than and greater than. And the best way to remember it probably is that the inequality always opens towards the side that is bigger. All right. And then you've also got the or equal to symbols. So you've got less than or equal to and greater than or equal to. And those are denoted by the same less than or greater than symbols, but they have essentially the bottom half of the equal sign. So it's like you take the top part of the equal sign and you replace it with one of the inequality symbols. Now, as we start solving these inequalities, for the most part, the procedure is exactly the same as solving an equation. You can add the same number to both sides, you can multiply both sides, so on and so forth. There is one major difference, however, and that is if you multiply or divide both sides of an inequality by a negative number, the direction of the symbol in the middle flips. So let's take an example. Let's say that 1 is less than 2. I think we can all agree that that's true. 1 is a smaller number than 2. That is further to the left on the number line. That's what it means to be less than something else, further to the left. If, on the other hand, however, we multiplied both sides of this by -1, we would now have -1 and -2, but we would need to flip the direction of the sign in the middle. That would be like saying -1 is greater than -2, and let's think about that. On the number line, -1 is further to the right, so it is true that -1 is greater than -2. All right, just because 2 is a bigger number, don't assume that when you're dealing with negative numbers, that's still the case. Everything kind of flips on its head. Now, once we take one of these inequalities and we solve it for our variable, we have to know how to interpret what something like x is greater than 8 means. And so there are going to be a couple different ways that we represent our solution. The first is in what is called interval notation. And the second is by a graph on the number line, which I will fill out as we go. So let's start with the different types of unbounded intervals we're going to come across. So if you had something like x is greater than a, so my example up here of x is greater than 8, then on the number line, that's like saying the solution, x greater than a, is all of the stuff bigger than a. So we would shade everything to the right greater than a. As an interval then, that would be from a, forever to the right, to positive infinity. Now for a strict inequality symbol like this, x is strictly greater than a itself is not a solution. If you've got something like x is greater than 8, that means that x can't be equal to 8. It has to be bigger. And so we represent the fact that the endpoint is not included with a parenthesis. And so this would be the open interval, it's called. It's open if you have a parenthesis at the endpoint from a to infinity. And we use the same symbol on the graph. So I would use an open parenthesis, opening in the direction of the solution. If we flip this and instead said that x is less than some number, x is less than a, then now on the number line, the solution would be everything less than a or everything to the left on the number line. So we're headed in the opposite direction this time. Remember, smaller numbers are to the left, bigger numbers are to the right. Once again, this is a strict inequality symbol. A itself is not part of the solution. This is an open interval. And I'll indicate that on the graph with an open parenthesis, opening in the direction of the solution. Now, in interval notation, it's something important to keep in mind is that you always read from left to right. This solution is headed towards negative infinity. Every now and then I'll see students write this as a to negative infinity, but that's not technically correct. You always read left to right. So this would be the interval from negative infinity to the right endpoint of a not included. If we change this up a little bit though, and now let the endpoints be part of the solution, so if we've got something like x is greater than or equal to a, we need a way to indicate that in our interval notation as well as our graph. And the way we do that is we swap from using a parenthesis to a square bracket. The idea being the endpoint is part of the solution now. If you have x is greater than or equal to 8, x can be 8 because of the or equal to part. And so this is called a closed interval because this time the endpoint is included. The idea is still the same. Greater than a would be everything to the right. But to indicate the or equal to, we now use a square bracket, opening in the direction of the solution. Similarly, less than or equal to a would be a and everything smaller. Everything to the left, so that would be from negative infinity to a with a bracket. And then if you had all real numbers, that's the entire number line. So the solution is just the entire number line. And as an interval, that would be forever to the left at negative infinity, to forever to the right at positive infinity. And that would be classified as an open interval because there's no closed endpoint like in the previous two. Now it is important to note that by convention, a is represented with either parentheses or brackets, depending on whether it's part of the answer or not, but you always use parentheses for infinities no matter what. And the reason for that is because infinity is more of a concept. It's not a number that you can ever actually reach. If you think of the biggest number you possibly can, once you write it down, I could just add 10 to that to get a bigger number. You can never actually get to that right endpoint or that left endpoint. So we're going to start off by solving something called simple linear inequalities. They're called simple to differentiate them from the compound inequalities that we're going to talk about later on in the section. And they're linear, so we're not going to have any x squareds or x cubes or anything like that. And so we're really just going to solve these like an equation. We're going to get x not equal to anymore, but x greater than equal to, isolate the variable. And then once we've got it like that, we're going to graph the solution and write it in interval notation. So starting with part A of example 1 here, if we've got -1 minus 4x is greater than or equal to 7, I want to solve for x, get x by itself. So if I start by adding 1 to both sides, we get -4x is greater than or equal to 8. And then I want to divide both sides by -4 to get the x by itself. But be careful, because I'm dividing by a negative number, the direction of the sign in the middle flips. So instead of greater than or equal to, it's now less than or equal to. And then 8 divided by -4 would be -2. Let me show you another way that you could solve the same inequality that would have avoided having to flip the thing in the middle. If I instead had added my 4x over to the right, and then subtracted 7 from both sides, we would have gotten -8 greater than or equal to 4x. And then if you divide both sides by +4, because you're dividing by a positive number, you don't flip the direction of the sign in the middle. It's only multiplication and division, and then on top of that, it's only with negative numbers. And so you would get negative 2 is greater than or equal to x, which is the same as saying x is less than or equal to negative 2. These are equivalent. Anytime you want to flip the order that you read the inequality in, the symbol flips with it. So saying 2 less than 3 would be the same as reading in the other direction, 3 greater than 2. All right, but this really just illustrates that we really had to flip the direction of the inequality when we divided by that negative number, or we would have gotten something different than if we had solved it in this other method. So now that we've got the answer, let's graph it and write our answer in an interval notation. So we've got x is less than or equal to negative 2. So remember, smaller numbers are to the left on the number line. So my answer is going to be negative 2 and everything less than or equal to. So all the stuff to the left, and because this was an or equal to symbol, we get a square bracket instead of a parenthesis. And it always opens in the direction of the solution. So this would be the graph of the solution. And in interval notation, this would be the interval from negative infinity up to negative 2 with a square bracket. Whenever you're graphing solutions in inequality, you don't have to be too careful about labeling a lot of your number line. All you need to do is put the important points on there. And for simple linear inequalities, it's usually just a single number. When we get to compound inequalities a little bit later on, we'll have to graph a couple of numbers, and at that point, it's only important to make sure that they're in the right order. So if you wanted to plot negative 1 and 2, you would make sure that you did negative 1 to the left of 2. All right, so now that we've got a taste of solving simple linear inequalities, try pausing the video here and see if you can both graph and write the solution in interval notation to part B. All right, so this is correspondent to a rational equation because we've got all of these fractions in the mix. So just like when we were solving rational equations, we can simplify this by multiplying everything by the least common denominator of 2, 3, and 4. So we need the smallest number that all three divide into, and that happens to be 4 times 3, or 12. So I'm going to multiply both sides of this equation by 12. All right, so when we distribute it through, we get 12 times 1/2, which is 6, minus 12x is greater than, I'm multiplying by a positive number, so I don't flip the direction of the symbol. 12 divided by 3 would give us 4 times x, and 12 divided by 4 would give us 3. And so now we go back to having just a simple linear equation. All right, I'm going to move the x's to the right this time, just for a little bit of variety. So if I add 12x to both sides, I get 6 is greater than 16x, 12 plus 4, plus 3. If I subtract 3 from both sides, we get 3 is greater than 16x. And then if I want to get x by itself, now I just divide both sides by 16. And I get 3/16 is greater than x. Now, you might find it easier, especially when you're starting out, when graphing and writing these in interval notation, to always put the variable on the left for the final answer. So I'm just going to flip this. This is the same as saying x is less than 3/16. So I'm going to start by graphing. Only point of interest in this case is 3/16. And our solution is that x is strictly less than 3/16. So to the left again, smaller numbers are to the left. But this time, because it's strictly less than, we've got a parenthesis instead of a square bracket. So this would be the graph of the solution. And in interval notation, that would read as negative infinity up to positive 3/16 with a parenthesis. One final time, let's solve one more simple linear inequality, and once again, try pausing the video and see if you can find the solution to part C of example 1. All right, so our goal is to get x by itself, which means we're going to have to start off this problem by multiplying that denominator away. So I'm going to multiply both sides by -7. On the left-hand side, this has the effect of just canceling out the denominator. So we still have 5 minus 3x. On the right-hand side, we get 0 times -7, which is still 0. So you'll notice not a lot really changed here, but we still multiplied by a negative number, which means the direction of the sign in the middle needs to flip. Now I need to solve for x, so if I subtract 5 from both sides, we would get -3x is less than or equal to -5. And then if I divide by the coefficient of -3, the sign in the middle flips a second time to go back to being greater than or equal to, and a -5 divided by a -3 would be a positive 5/3. So we get x is greater than or equal to 5/3. As a graph, this is greater than this time, so that's the numbers to the right of 5/3, bigger numbers. And because it's an or equal to symbol, we use a square bracket for 5/3 itself. And in interval notation, that would read as the interval from 5/3 with a square bracket to positive infinity, and infinities always have parentheses. So for the next type of problem we're going to be working, which are called compound inequalities, we're going to be combining multiple simple inequalities together, which is going to change things a little bit, because now we're going to sometimes at least end up with what are called bounded intervals. Now, the previous set we looked at were called unbounded intervals because they were always headed forever to the right to positive infinity or forever to the left to negative infinity. So that we would say that it would be increasing or decreasing without bound. It just keeps getting bigger forever. It keeps getting smaller forever. That's not necessarily going to be the case this time. It's possible that we will have our solution trapped between two values, two numbers. And if that's the case, it's now called a bounded interval. But the idea is kind of the same. If your solution is trapped between a and b, so you've got something like x is greater than a, but x is less than b, then graphically speaking, you've got a to the left, b to the right. The solution is all the stuff in between. And because these are strict inequality symbols, once again, we use parentheses for the endpoint. So this would be the open interval from A to B. If you swap the symbols out for or equal to, well, that just means that the endpoints are now included. So all the stuff in between A and B, but A and B themselves are part of the solution this time. So square brackets, this would be what is called the closed interval from A to B. But mixing it up a little bit, you can actually have a mix of symbols this time around. So if x has to be strictly greater than a, but less than or equal to b, then because the strict symbol is associated with a is not part of the solution, so parentheses for it. The or equal to symbol is paired with b, so b is part of the solution, square bracket with it. So parentheses for a, bracket for b. This is now called a half open interval or a half closed interval. Either one works. Important to note that you couldn't have half open or half closed intervals with the unbounded intervals we looked at before. Instead, they were called open or closed purely by the endpoint that wasn't the infinity. This time, both endpoints have a bit of an influence in the name of open or closed. And similarly, if the or equal to is now part of the A, it gets the square bracket because it's part of the solution. And if B has the strict inequality symbol, it gets the parentheses because it is not part of the solution. And so that would be from A included to B not included. And this one would have the same name of half open or half closed. So now let's talk about compound inequalities. Compound inequalities are going to be two or more simple inequalities. We're primarily just going to be dealing with two, but you could extend the idea to more, joined by the connective word and or. So you might have x is less than 3 and x is greater than 4, for example. You could have x is less than 3 or x is less than 4. These would be compound inequalities. And the word that you use to join the two is very important because it changes the meaning of the compound inequality. So we're going to start off by talking about and compound inequalities. And the idea is that the solution interval to an and inequality are all of the numbers that satisfy both at the same time. That's what the word and means, both. So in order to be part of a solution to something like x is less than 3 and x is greater than 4, it would have to be a number that is both less than 3 and greater than 4. You're looking for the numbers that meet both conditions at the same time. So in order to find that, one approach that we can take, because it's not always going to be as simple as just looking at it, is that you can actually solve both linear inequalities separately and then graph their solutions above the number line. So if I had x is less than 3, that would be all the numbers smaller than 3. If I had x is greater than 4, that would be all the numbers greater than 4. Then the numbers that satisfy both inequalities are where the two solutions overlap with each other. In this case, these solutions don't overlap at all. So this would be an example of a compound inequality with no solution, which happens sometimes. But the overlap between the two will be your final answer to the and compound inequality. That will be the region where the numbers satisfy both inequalities at the same time. Now, this is going to come up a little bit later on in the course, so it's important to note that we have a name for this operation. Anytime you're looking for where two intervals overlap with each other, that is called an intersection of the two intervals. And the symbol we use for that looks kind of like an upside down capital U. And an intersection by definition is where the intervals overlap with one another. So for now, we're going to be solving simple linear inequalities and looking for where their solutions overlap. But later on in the course, if we're just asked to take an intersection, the procedure will be the same. You'll just graph this on a number line, graph this on a number line, look for where they overlap. So let's take a look at some and compound inequalities. And for each, we're asked to graph the solution and write the solution in interval notation, just like in example 1. So to start off with, we've got 5 minus x is less than 4, and 0.2x minus 5 is less than 1. So to start off with a compound inequality, you start by solving both simple inequalities for x. So it's like two problems from example 1. So starting with the one on the left, 5 minus x is less than 4. If I subtract 5 from both sides, we get negative x is less than negative 1. And then if I multiply both sides by negative 1, it flips the direction of the sign in the middle, and I get x is greater than 1. For the one on the right, if I add 5 to both sides, we get 0.2x is less than 6. And then if I divide by 0.2, we get 6 divided by 0.2, which you could use a calculator to help out with. But if I multiply both the top and bottom of that fraction by 10, that would be the same as 60 divided by 2, or 30. So this is x less than 30. So these are the two solutions to the linear inequalities. This is equivalent to x is greater than 1 and x is less than 30. So let's figure out where that applies to. For x is greater than 1, that's going to be 1 and all the stuff to the right, everything greater. For x is less than 30, that would be all the things smaller than 30, 30 and less. And so the overlap of these two intervals is going to be the region in between 1 and 30. That does beg the question of what about the endpoints themselves, though? Remember, to be a solution to the final and inequality, it has to be on both number lines. So while the number 1 is a solution to x less than 30, it's on that bottom graph. Because of the open parentheses, it is not a solution to x greater than 1. It's not on that top graph. And so since 1 is not on both, the parentheses just carry down. The same is going to be true for the 30. It's part of the top solution, but not the bottom. So we get parentheses for it as well. So this is the final graph of the solution. This is the bounded open interval from 1 to 30. So let's take a look at another and compound inequality, and try pausing the video here and see if you can find the solution to part B of example 2. Okay, so once again, the first step is always to solve the simple linear inequalities individually. So for the one on the left, if we multiply both sides by 2, don't flip the direction because we multiplied by a positive number. If I subtract 4 from both sides, and then if I multiply both sides by -1, now the direction does flip. So that would be the same as x less than 2. For the one on the right, if I want to get rid of that denominator of -3, I'm going to multiply both sides by -3, which just cancels out the denominator on the left, and 1 times -3 would be -3, but because that's a negative number, instead of less than, it's now going to be greater than. Now I'm going to add 9 to both sides. -3 plus 9 would give us 6. And then if I divide both sides by 2, we get x greater than 3. So our compound inequality is x less than 2 and x greater than 3. All right, so let's think about this. And you might be able to figure out what's about to happen just by thinking about less than 2 and greater than 3. X less than 2 would be 2 and everything less. X greater than 3, or excuse me, not 2, parentheses. And x greater than 3 would be everything to the right of 3. So in this case, there is no overlap. There are no numbers that are both less than 2 and greater than 3. So there's no solution. So a couple different ways to write that. You could type out, or you could write out no solution. As far as a graph goes, it would just be a graph with nothing shaded. And you can also write this as, of course, the empty set symbol, the 0 with the slash through it. Now let's talk a bit about special notation. For and compound inequalities in particular, there's special notation you can write it in that basically leaves your variable sandwiched between two other values. So for example, if we had, back in part A of example 1, we had x greater than 1 and x less than 30. You could actually combine that together, and you can always see if it's possible to combine based off of the graph of your solution. Our final answer was all the stuff in between. So x is greater than 1 and less than 30. So this is basically equivalent to saying your x is trapped between 1 and 30. Now, a couple things to note about this notation. First things first, it only works for and compound inequalities. So in a few minutes, we're going to start talking about or compound inequalities. Those have no special notation. You can't join those together. And on top of that, it only works if x is both bigger than something and smaller than something bigger. So it only works if your solution would be trapped between two values like this. So there are even a lot of and compound inequalities that can't be joined together with this special notation. So for example, on the previous slide, we had x less than 2 and x greater than 3. Right? That doesn't work. You can't combine that together in the shorthand notation. If you tried it, 3 is the thing smaller than x, so 3 is less than x. X is less than 2, but this doesn't make any sense because this is implying that 3 is less than 2, which is not. Those don't combine, so be careful. In fact, I would recommend that maybe you just don't try to join inequalities together yourself with this notation until after you graph the solution, and then you might want to. But if you're given an inequality in this notation, it actually makes it a lot easier to work with. Because what we can do is we can solve both parts of the inequality at the same time. The idea is very similar to solving an equation. So if you've got something like 2x is equal to 6, you divide by 2, but you're careful to divide both parts of the equation by 2 to keep everything balanced. The same thing's going to be true here. If I want to do something to this middle part of the inequality, I need to do the same thing to all 3 parts of the inequality. So let's work with it in this notation. So if I want to solve for x, I need to subtract that 9 away. So that means I'm going to subtract 9 from all 3 parts of this inequality. So that would give us negative 12 is less than or equal to 4x, which is less than or equal to 8. And then if I want to solve for x, I need to divide that coefficient of 4. So I divide all 3 parts of the inequality by 4. And because that's a positive 4, I don't swap the direction. If I were dividing by a negative number, the direction of both would flip. And so I get negative 3 less than or equal to x, which is less than or equal to 2. And so this is the simplified form of the compound inequality. And again, you could write this as and notation if you wanted to. This is the same as saying negative 3 is less than or equal to x, and x is less than or equal to 2. But the thing that is so powerful about this notation is that it basically tells you exactly what the graph is. You don't have to graph them both and look for the overlap. This is just saying that x is trapped between negative 3 and positive 2. So if I were to graph this, negative 3 is further to the left on the number line. So x is greater than negative 3, but less than 2, the stuff in between. And because both of these inequality symbols are or equal to's, the endpoints will be included. So this would be the interval, the closed interval, from negative 3 to 2. Let's take a look at one more and inequality in this special notation. And now that you've seen an example of it, try pausing the video here and see if you can find the solution to part D of example 2. right, so once again, my goal is to get the x in the center by itself. So I need to get rid of this positive 5. So I'm going to begin by subtracting 5 from each side of the equation, or from all three parts of the inequality, rather. That would give me negative 18, strictly less than negative 9x, which is less than or equal to 36. And now I got to get rid of that coefficient of negative 9. So I'm going to divide all three parts by negative 9, which would give me a positive 2, an x, and a negative 4. But because I divided by a negative number, the direction of both symbols flip. So we get 2 is greater than x, which is greater than or equal to negative 4. Or if you want to read that backwards, it would be the same as saying negative 4 is less than or equal to x, which is less than 2. And so if we want to graph this solution on the number line, this is the interval from negative 4 to 2. Brackets for the negative 4 because of the or equal to. Parentheses for the 2 because of the strictly less than symbol. And so this would be the half open or half closed interval from negative 4 to 2. So now let's talk about the other type of compound inequality, and those are or compound inequalities. And so let's say we have something like x is less than 2 or x is greater than 3. Well, this is quite different from the and. In order to be a solution to the and inequality, you had to be a solution to both. Both had to be true at the same time. Whereas when you use the word or, you're less picky. All you have to do is be a solution to one of the inequalities, and that satisfies the word or. So any number that satisfies the one on the left is part of the final answer. Any number that satisfies the one on the right is part of the final answer. Any number that satisfies any of the inequalities is part of the final answer. And so this time around, in order to figure out what the final solution is, you still start the same way by solving both simple inequalities, which I've already done in this case. These are already simple inequalities to begin with. With and inequalities, we plotted both solutions and looked for the overlap. But with or inequalities, you can just plot both solutions. All the stuff less than 2 is part of the final answer. All the stuff greater than 3 is part of the final answer. So all you have to do is graph all of the solutions on the same number line. Anything that ends up shaded is part of the final answer. Anything that doesn't end up shaded is not, right? 2.5 wouldn't work because it's not less than 2 and it's not greater than 3. It doesn't satisfy either inequality. And so let's talk about how we split this up. This process of joining intervals together, so the solutions for x less than 2 would be negative infinity up to 2. The solution for x greater than 3 would be 3 to infinity. Our final answer is both of these joined together. So whenever you join intervals together, that is called a union of intervals. And the symbol we use for that looks a little bit like a capital U, U for union. Whenever your final answer has a gap in it like this, we join the parts of the solution together with that union symbol. All right, so again, to recap, for an or compound inequality, solve both simple inequalities first, and then just plot the solutions on the same number line. Anything shaded is part of the final answer. Anything that isn't shaded isn't. All right, so in example 3, we've got the compound inequality 5 plus x is greater than 3 minus x, or 2x minus 3 is greater than x. So we're looking for all the numbers x which would make either one of these true. As long as at least one is true, we're good to go. So I'm going to start by solving both simple inequalities. For the one on the left, if I add x to both sides, we've got 5 plus 2x greater than 3. If I subtract 5, 2x is greater than negative 2, so if I divide by 2, we get x is greater than negative 1. The direction doesn't flip because I'm dividing by positive 2. On the right-hand side, if I subtract x from both sides, x minus 3 greater than 0, add 3 to both sides, x is greater than 3. So we've got x is greater than negative 1, or x is greater than 3. So x is greater than 3 would be everything to the right of 3. X is greater than 1 would be everything to the right of 1. So that's going to be together everything to the right of 1. But what about the parentheses at 3 itself? Well, it wasn't a solution to one of the inequalities, x greater than 3, but it was a solution to the other, x greater than negative 1. Because the solution for one inequality went through the parentheses, 3 got shaded. It is part of the final answer. So our answer here, and you could even do away with that parentheses altogether. So our answer here would be the interval from negative 1 to positive infinity. Essentially, everything that satisfies this inequality, something that's bigger than negative 1, or rather in reverse, anything that satisfies this inequality, something that is bigger than 3, automatically satisfies this one as well. And so we got a bit of overlap between the two. By the way, if you had changed this to an and inequality, what would the solution have been in that case? Instead of negative 1 to infinity, the overlap would have been from 3 to infinity, really illustrating the point that you have to treat and or compound inequalities differently. The solutions are not the same. All right, so let's take a look at another. Try pausing the video here and see if you can find the solution to part B of example 3. Okay, so once again, I want to start by solving the simple inequalities. For the one on the left, to get rid of that 1/2, I'm going to multiply both sides by 2. So that would just cancel out the 1/2 on the left and give us x plus 6 is greater than 6. If I subtract 6 from both sides, that would give me x is greater than 0. For the one on the right, I could divide the 4 away, but that would make things a little bit messy. So instead, I'm going to go ahead and just distribute it through to get 4x minus 4 is less than 3x minus 4. If I add 4 to both sides, those minus 4's basically cancel each other out. And then if I subtract 3x from both sides, I'm going to get x less than 0. All right, so we've got x greater than 0 or x less than 0. So let's think about that. We've got x greater than 0. That would be 0 and everything to the right. We've got x less than 0. That would be everything to the left. And excuse me, earlier it was not 0 and everything to the right. It was just everything to the right. Which means anything smaller than 0 is part of the solution. Anything bigger than 0 is part of the solution. But as for 0 itself, it's not a solution to x greater than 0, and it's not a solution to x less than 0. It has parentheses on both. So it is actually not part of the final solution. And so in interval notation, this would be the interval from negative infinity to 0 with parentheses not included, along with the interval from 0 to positive infinity, And because it's broken up into two parts, it has to be, because 0 is not a solution, we are going to join those together with the symbol for union, which looks kind of like that capital U. Now, the last type of problem in this section is by far the trickiest, absolute value inequalities. And that's because it's basically one step extra on top of the compound inequalities that we were just working. So absolute value inequalities will always simplify to either an and compound inequality or an or compound inequality. And let's think about the setup here, because the setup is by far the hardest part. So let's say you have some constant k greater than 0, because we're dealing with absolute values here. If you have the absolute value of some expression u greater than k, think about what absolute value is by definition. It is distance from 0 on the number line. So what you're saying here is that the distance has to be greater than some value k. So as an example, let's say we had absolute value of x greater than 2. What you're saying is that distance from 0 has to be bigger than 2, which means it would have to be further to the right of positive 2 or further to the left of negative 2. Right? Anything from here is further away than 2. Anything from here is further away than 2. And so it is distance beyond the positive and negative version of whatever k is. And so this ends up being an or compound inequality. So we say that u is less than the negative version of k, or u is greater than the positive version of k. And again, if you're ever confused as to what the setup is, think about what it means. Absolute value is distance. This is distance greater than k, further away than k. For the second type of absolute value, let's say you still had the same positive k, but now the absolute value is less than k. So now what you're saying, if you had something like absolute value of x is less than 2, is that the distance is less than 2. Distance smaller than 2. So that means you're saying that it has to be closer to 0 than 2. Distance less than 2 from 0. And so this ends up being then an and compound inequality, but you don't have to write it in terms of and. With absolute value in particular, it always ends up being this bounded interval, trapped between negative k and positive k. So this is an example where that special notation really comes in handy. Although it is, at its heart, a compound inequality. Negative k less than u and u less than k. Now keep in mind this is only defined for where the number k is positive. If it's negative, then all you have to do is think about it. So let's say you had absolute value of x greater than negative 2. You're saying that the absolute value is bigger than a negative number. Right? So think about what you could plug in for x that would make this true. If you plugged in 1, absolute value of 1 is bigger than negative 2. If you plugged in negative 10, absolute value of negative 10 would be positive 10, which is greater than negative 2. No matter what you plug in for x, an absolute value will always be bigger than a negative number. So if you have absolute value greater than a negative number, the answer is all real numbers, or from negative infinity to positive infinity. Whereas on the other hand, if you had the absolute value less than a negative number, well, this absolute value will always be 0 or positive. So when is it smaller than a negative number? The answer is never. So in this case, it would be no solution. So again, just kind of reason it out. When is an absolute value bigger than a negative number? Always. When is an absolute value smaller than a negative number? Never. So let's work some absolute value inequalities. Starting with part A in example 4, we've got the absolute value of x plus 2 greater than 5. So again, for the setup here, I'm going to do a u substitution to make it a little bit easier to see. So we're saying distance greater than 5 from 0 further away than a distance of 5. So this is going to be everything inside of the absolute value, because it would be u less than negative 5 or u greater than 5. So x plus 2 less than negative 5 or x plus 2 greater than positive 5. This is not the final answer. This is just the setup, because this plus 2 here is going to shift things around. So now, if for both of these I just subtract 2, I'm going to have x less than negative 7, or subtract 2, x greater than 3. So if I plot this, x less than negative 7, x greater than 3. Basically, that plus 2 in parentheses ended up shifting this bit 2 to the left when all was said and done. And so in interval notation, that would be from negative infinity to negative 7, from 3 to positive infinity, with the union symbol in between. For part B, we've got the absolute value of 6 minus x less than 6. So again, I'm just going to swap it out for you to help with the setup, because this is not something that you should try to brute force memorize. This is something you should understand so that it sticks with you. And so now we're saying distance less than 6. Closer than 6. Now, one thing to note here is that in the previous slide where I was giving the explanation for these, I only used strict inequality symbols, but it would work the same way if you had or equal to. It would just then include the endpoints instead of excluding them. So same idea. But in this case, we've got strictly less than 6. So if this is in terms of u, u would be trapped between negative 6 and positive 6. So it's greater than negative 6, but less than positive 6. But u is 6 minus x. So we've got negative 6 less than 6 minus x less than positive 6. An and compound inequality. Now I want to solve for x. So I'm going to start by subtracting 6 from all three parts, which would give me negative 12 less than negative x less than 0. And then I need to divide all three parts by negative 1 to get a positive x. But that's going to flip the signs in the middle. So that would give me 12 greater than x greater than 0. Or if I still want to read it left to right, 0 less than x less than 12. All right, and so if I were to graph this, we're going from 0 to 12, endpoints not included. Everything in between. Or in interval notation, 0 to 12 with parentheses. By the way, you can always double check your answers by taking a point in this interval. So you want anything between 0 and 12, say like 4, and plugging it back into the original inequality to see if it makes it true. If you plugged in 4, you would get the absolute value of 6 minus 4, which is 2. Is that less than 6? The answer is yes, it works. Whereas if you pick something outside of your solution interval, it should make something false. So let's say we plugged in -1. You would get the absolute value of 6 minus -1, which would give you the absolute value of 7 or 7. 7 is less than 6 is false, which is what we want to see because that was not part of the solution interval. For part C, we've got 3 less than absolute value of 2x minus 1. For the sake of the setup, I think it really helps to have the absolute value on the left. So I'm just going to swap the order of this and write absolute value of 2x minus 1 is greater than 3. So try pausing the video here and see if you can find the solution to part C of example 4. All right, so we've got distance from 0 greater than 3 again, beyond 3. So that means the stuff inside parentheses, 2x minus 1, would have to be less than -3 or greater than +3. I'm going to add 1. That would give me 2x is less than -2, which if I divide by 2 would give me x is less than -1. On the other one, if I add 1, I get 2x is greater than 4. If I divide by 2, I get x greater than 2. So we've got x less than -1 or x greater than 2. X less than -1 or x greater than 2. Which in interval notation, we would have -infinity to -1, union +2 to +infinity. Part D is similar. The only difference is now the absolute value is not isolated. So we've got 3 times the absolute value of x minus 1 plus 2 is less than 8. And just like when we're solving absolute value equations, these absolute value bars you cannot cross. You can't multiply through. It just is the way it is. So the first thing you're going to do is isolate the absolute value, and then it becomes exactly like the other 3 problems. So with that said, try pausing the video here and see if you can find the solution to part D of example 4. All right, so if I want to get the absolute value by itself, I'm going to start by subtracting 2, which would give me 3 times the absolute value of x minus 1 is less than 6. And if I divide that coefficient of 3 away, we've got the absolute value of x minus 1 is less than 2. Distance less than 2. Closer than 2. And you know what? Just for the sake of variety, this time around, let's make this entire problem or equal to. All right, and so that means that our thing inside of the absolute value, x minus 1, has to be greater than or equal to the left endpoint -2, less than or equal to the right endpoint of +2. Now I'm just going to add 1 to all 3 parts of the inequality. To get -1 less than equal to x, which is less than or equal to 3. Endpoints included this time. All the stuff in between. So this would be the closed interval from -1 to +3. And then last but not least, part E of example 4, we've got the absolute value of 3x minus 7 greater than or equal to negative 5. Distance from 0 greater than negative 5. So again, because this is a negative number and the absolute value is already isolated, just puzzle this one out. When is an absolute value bigger than a negative number? The answer is always. So the solution would be all real numbers, which as a graph would just be the entire number line shaded. Not a very helpful graph. Or an interval notation would be from negative infinity to positive infinity. And that is it for section 1.7 on inequalities. So this is a section that very much builds off of itself. So the bottom type of problem, absolute value inequalities, is actually just a combination of the previous problem types. So we started off by solving simple inequalities. Then we moved to compound inequalities, and each one is a little bit different. So make sure you know how to handle both and compound inequalities and or compound inequalities. And simple inequalities is part of that process because you've solved those as part of solving the bigger compound part. And then you've got the absolute value inequalities. Make sure you know the setup for those. It's the trickiest part of this section, but again, trying to remember it in terms of distance greater than, further away, or distance less than, closer to, can really help you remember how the setup for those problems looks. With that said, as always, if you guys have any questions, please let me know, and I will see you in the next video.